Welcome back to our Introduction to Causal Inference course. This is part 3 of lecture 2. In today's video, we're going to continue our discussion about DAGs, this time presenting very important concepts for the application of DAGs for causal inference, the concepts of deconnection and deseparation. We ended our last video talking about open paths. So now I want to describe when a path is open, when a path is not open or blocked, and what does all that even mean. So as we are going to learn in this video, there is a set of rules that allow us to detect which paths in a DAG are open and how we can block them if we want to. And I know I am yet to explain what an open path is. I'm going to do that over the next slides. But what I want to say now is that if two nodes or two variables in a DAG have at least one open path between them, they are said to be deconnected. Otherwise, that is, if there is no open path between them, those nodes or those variables are said to be deseparated. So deconnection means at least one open path, and deseparation means no open path. And what is the intuition that we want to understand and apply to our DAGs? Is that non-causal paths between X and Y that are open, they connect X and Y. They are sources of association between X and Y, but this association comes from mechanisms other than the effect of X and Y because they are non-causal paths. So those are biasing paths. Those are paths that are sources of association between X and Y, but the mechanism that is driving this association is not the cause effect of X on Y. And our goal is to use the DAG and apply deconnection and deseparation rules to block biasing paths, but not causal paths. And the idea here is that if we can block all biasing paths, the only remaining source of association between X and Y can only be the causal effect. And of course, it is important to understand we are doing all this based on the assumptions encoded in a DAG. That is, once we use our prior knowledge or our prior assumptions to draw the DAG, then we can use the DAG to arrive at those conclusions. So of course, the validity of those conclusions are going to be 100% dependent on whether or not our DAG is true. So we are interested in the effect of X on Y. So we want to make sure that there is no source of association between X and Y other than a potential causal effect of X on Y, if any exists. And for now, we are assuming there is none, just to make the DAG simpler. So the first rule of deseparation is that the presence of a collider in a path blocks the path. So let us consider this example. We have X and Y, and we have one path between X and Y, the path X, Z, U, and Y. Is this path open? Is this path blocked? Well, this path is actually blocked because it contains a collider Z. So we would say that this path is blocked at Z, and since there is no other path between X and Y, we would say that X and Y are deseparated. It is easy to sort of memorize this rule, but I also wanted us to understand what this rule is actually saying. For some people, it's not very intuitive because we have a path, but this path does not induce an association between X and Y. How can that be? Well, if you think about what a collider means, it's actually not very difficult to understand why this rule actually applies. This rule simply means that the fact that two variables have a common effect does not imply that they are related. And if we think about it, if the fact that two variables have a common effect would produce an association between them, then there would be no independent causes of the same effect, right? Because if any two causes of the same effect have to be somehow correlated because they have a common effect, then it would be impossible for independent causes of the same effect to exist, which is of course not the case. So here consider the simple example where we have maternal smoking affecting birth weight and sex affecting birth weight. Would we say that maternal smoking and sex are correlated with one another just because they both affect birth weight? No, I mean, we would not say that. It is the fact that they both affect the same variable does not in any way imply that they are or that they are not related to one another. Of course, they could be. My point here is that if they are related to one another, it's not because they have a common effect. Now, the second rule of this separation states that if we have a collider in the path between, say, X and Y, and we condition on this collider, we open the path between its parental variables. That is, Before, we said that the presence of a collider blocked the path at the collider. But now we're saying that if I am conditioning on the collider, I am opening the path at the collider. And by conditioning, I mean any form of adjustment for that variable. It could be stratification, it could be inclusion as a covariate in a regression model, etc. So in our example here, the path between x and y was originally blocked at z, but now we are conditioning on z. Say we're restricting our analysis to a particular level of z. And I am indicating conditioning by a box around the variable. And since this path has no other collider, the path is now open. And the implication here is that x and y become deconnected through a non-causal path. Notice that this path does not describe the causal effect of x and y, because a causal path has the arrows always in the same direction, which is not the case here. So the implication here, as I said, is that x and y become deconnected through a no-causal path. And even though x and y were marginally disseparated, that is, they were disseparated if I don't do any conditioning, any adjustment, they become conditionally deconnected. Even conditioning on z, x and y become deconnected because now there is an open path between them. And there is a second part to rule 2, which is that adjustment not only for a collider, but also for a descendant of a collider also opens the path between the parents of the collider. So for example, here we have the path, again, x, z, u, and y, and we have z2, which is a descendant of z, and we are conditioning on z2 as indicated by the box around z2. And according to rule 2b, we would say that the path between x and y is now open at z because we are conditioning for a descendant of the collider z, and because the path contains no other collider, then we would say that x and y are deconnected given z2. And it might seem weird at first that a collider that's not being adjusted for blocks the path, but now a collider that is being adjusted for opens the path. So let us think about it for a second. Why adjusting for a collider opens the path? And let us use an example to try to understand why this is the case. Suppose we are interested in the relationships among the price of a house, the location of a house, and the size of a house. And for simplicity, we will assume that there is no correlation between location and size. That is, the proportion of larger and small houses is the same across different neighborhoods. So this will be our DAG. We have the location, which influences the price, and the size, which influences the price. So notice here that location and size are independent in our DAG because price is a collider that's not being conditioned on. But now let us condition on price, and let us do that by restricting our attention to cheaper houses. That is, we are restricting our analysis to a given level of the collider price. So what happens when we only look at cheap houses? If you have a cheap house that is in a very good location, it will most likely be small, otherwise it wouldn't be cheap. Similarly, if you have a cheap house that is big, it will most likely be in a bad location, otherwise it wouldn't be cheap. So in this example here, we have two positive causes of the collider price, in the sense that a better location causes a higher price, and a bigger size causes a higher price. But when I conditioned on price and I looked only at cheap houses, I induced a negative correlation between the two causes of the collider. So now let us consider the separation rule 3. And this rule says that adjustment for at least one non-collider blocks the path between its parental variables. That is, we would say that the path is blocked at the non-collider. So consider the path x, u, and y. We can see that there is a path between x and y. This path is open because it contains no collider, and it is a non-causal path because it is not pointing from x, it is pointing into x. So how could we block this non-causal, this biasing path? We could block it according to rule 3 by conditioning on u, that is by adjusting for u. This would result in x and y being conditionally deseparated. So x and y are marginally deconnected through this no-causal path, but they become conditionally deseparated given adjustment for the variable u. The examples we just considered illustrate a more general fact about the implication of conditioning on a given variable with regards to its role in a given path. So if the path was marginally open at that variable, it becomes conditionally blocked at that variable once we condition for that variable. And this is the case of non-colliders. However, if the path was marginally blocked at the variable, it becomes conditionally open at the variable once we adjust for that variable, and this is the case of colliders. And now that we learned the deseparation rules, you should be asking yourselves, okay, I know deseparation rules and how I can apply them to a DAG, but when I have data, I don't know what is the true DAG. All I can extract from the data is statistical patterns. So the question is, how can we use the deseparation rules we just learned to guide our interpretation of statistical patterns we see in the data? And we do that using two other rules that relate the separation and the connection to statistical associations. And those rules are compatibility and faithfulness. What is compatibility? Compatibility means that if we have this separation, we have statistical independence. In other words, if there is no open path between two variables, there will be no statistical association between them. So in our example here, we have x and y, and x and y are deconnected through the path x, u, m, and y. And if we block this path by adjusting for u, for m, or for both of them, x and y will no longer be deconnected. They will be deseparated, and by compatibility, they will not be statistically associated. And this rule is quite intuitive. It just says that if there is no source of association between two variables, after all, an open path is a source of association, then we would not expect those two variables to be associated. And the second rule is faithfulness. And faithfulness says that deconnection implies statistical association. In other words, if there are two or more open paths between two variables, these variables will typically, and I underline this word for a reason, be statistically associated. So here in our example, we have x and y deconnected again through the path x, u, m, and y. And since x and y are deconnected, unless we block this path by conditioning on u or m or both, x and y will likely, and again, I underline this word here, be statistically associated. In other words, if I have a source of association between two variables, that is, if I have an open path between two variables, then I would expect them to be statistically associated. But why did I underline the words typically and likely here? It is because we can talk about two versions of faithfulness: strong faithfulness and weak faithfulness. Strong faithfulness says that the connection is equivalent to statistical association. That is, if I have one or more two open paths between two variables, those variables will be statistically associated. While weak faithfulness makes a weaker statement. Weak faithfulness postulates that the connection simply does not allow us to exclude the possibility of statistical association. So it does not guarantee that there is a statistical association, but it says it might be, you cannot say that there isn't. So we're not claiming that the two variables are associated. We're just saying they might be. We cannot guarantee that they're not associated. So why do we have weak faithfulness? It might be intuitive at first to think that, okay, if I have two or more open paths between two variables, I have sources of association between them, so I would expect them to be associated. But it turns out that this is not always the case. So let's consider a very simple example of this, where we have two paths connecting x and y, the causal direct effect x, y, and the causal mediated effect x, m, and y. It is possible, for example, that the mediated effect is positive, the direct effect is negative, and those effects have the same magnitude, so they end up canceling out, so that the total effect of x on y is actually zero. So here we have a situation where we have the connection because there are two open paths between x and y, but those open paths ended up canceling each other out. So this is what I had to say about the connection, the separation, faithfulness, and compatibility. I hope this was clear to you. Stay tuned for the next video when you're going to apply those concepts to a DAG in order to identify covariates that we can use to eliminate bias in the association between X and Y. Stay tuned for that.